Hello everyone, this is Rui PCB, your trusted PCB partner. Today, our topic is six-layer boards and power integrity, how to build an unbreakable power network with multiple power planes and diverse power sources. Welcome back to the six-layer board power integrity course. In the previous video, we discussed the dangers caused by power ripple and ground bounce, as well as the limitations of four-layer boards in handling complex power requirements. Today, we turn our attention to six-layer boards to learn how to make use of them. We'll explore the advantages of multi-layer boards, especially how multi-power plane designs can help build an unbreakable power network. This ensures that our chips can receive a stable and pure supply of power. The stack-up structure of a six-layer board. How does it lay the foundation for an unbreakable power network? First, let's review our recommended stack-up structure for a six-layer board, which is asterisk D-type point, a CD structure like the D-type. Following this structure provides an excellent foundation for power integrity. First, it has two distinct ground planes, specifically layers L2 and L5, which are designed to provide a robust and exceptionally low impedance grounding system. Additionally, there is a crucial core power plane, designated as L4. This is the main power plane. The key sandwich structure, L5. The tight coupling between L5 and L4 forms a powerful decoupling capacitor. It's like a huge supercapacitor that can efficiently suppress power noise. It's these two layers, they are extremely close to each other. How do we set up multiple power planes on a six-layer board? How do they affect things? What about stability? In complex six-layer board designs, we usually need more than one power voltage. For example, 5 volts, 4.3 volts, and 1.8 volts. The multi-layer advantage of a six-layer board allows us to handle these voltages more flexibly. We can make detailed splits on the L4 layer. The main strategy is to divide the main power plane L4 into different voltage regions. For example, splitting L4 into such as plus 5 volts, plus 3.3 volts, and other regions. We can also take a look at our circuit here. Right now, I have selected the L4 layer, and you can see it has different regions. Let's take a quick look. For example, this region here is the analog 3.3 volts, labeled as 3.3 ATC, and then this region is for the 1.35 volt signal. This region is for the digital 3.3 volts. This is 7V33, and then this region is the main control line. So we can see that the chosen solution is to have multiple power supplies on the L4 layer. What effect does this have? This way it can provide independent low impedance power regions for chips with different voltages, preventing interference between them. In fact, this division is mainly based on their power distribution, which we can see on the test diagram. It's roughly this area. This is for the analog 4.3 volts, and this area is just a small part. Remember, this area is the digital triangle. The key point is that the dividing line must be at, keep the spacing below the L2 layer, and make the dividing line as short and wide as possible to avoid high-speed signals crossing the boundary line. It doesn't matter either way. How do we divide the power on the L4 layer? We must ensure there is a complete ground plane, just like the L2 layer, which always maintains its integrity and is never stitched or cut. Another method is to borrow ground from other layers, or borrow power, or even add more power layers. And then inside the side, for situations where the current demand is not high or there are many different voltage types, besides splitting the L4 plane, we can also within L1, L3, and L on the signal layers, as long as it doesn't affect, as long as the signals are not restricted, We can lay short and wide power lines and supplement them with a large number of decoupling capacitors, or use ground vias to form a localized small power network. This is often done in other projects, especially when the top and bottom layers are L1 and L6, where you can place some short distance power lines, like this example here. Here, some power lines are placed over a short distance. In this area, you can also see some power lines running to other places. What about more advanced strategies? That is, if the system is extremely complex with many types of voltages, if there are many types of voltages and high power consumption, you can even consider converting one of the signal layers, such as L3 or L5, into an additional power plane. This is another approach. So for a structure with two power planes, as we discussed earlier when talking about electrical structure, this reduces the available space for signal routing. How do these changes affect the stability of the power network? First, there is a stronger average capacitance effect. Each power region after segmentation still remains hidden, and below it, the ground plane below or the ground plane above. This forms a planar capacitance, which continues to provide decoupling and offers better isolation. Between different power regions, the separation helps with physical isolation, preventing noise coupling between areas of different voltages. What other golden rules are there for power plane design in six-layer PCB? The first rule is that the ground plane must be an unbreakable foundation. The L2 and L layers, especially L2, should be kept as intact and unsegmented as possible. They serve as the technical basis for all power and signal integrity. This circuit does a good job of fulfilling the first point. The ground on the LL2 layer is complete. Then, the ground on the L5 layer is divided into digital and analog sections, which ensures that there is always a complete ground plane present. This can provide a reference mechanism. The power supply and ground are tightly coupled, ensuring that the dielectric thickness between the power plane and the ground plane is as thin as possible in order to maximize the plane capacitance to suppress high-frequency noise. This is an issue to consider when selecting the board during PCB design. Choose a thinner one whenever possible. A large number of decoupling capacitors. No matter how excellent the power plane is, it is still essential to place a large number of decoupling capacitors with various capacitances at each IC power pin. These capacitors should be placed as close as possible to the IC and connected to the nearest power and ground planes through short, thick vias. This is also very obvious in the 3D diagram, especially above and below the core CPU, where a large number of capacitors of various sizes are placed. Fourth, avoid high-speed signals crossing power plane splits. To emphasize again, this is absolutely forbidden. The return path of high-speed signals will be interrupted, resulting in severe EMI and SI issues. Today, we took an in-depth look at multi-power plane design strategies on six-layer boards, learned how to implement power plane splits on layers like layer 4, and explored how such designs enhance the stability of the power network through robust shielding and isolation. We also emphasized the importance of ground plane integrity and decoupling capacitors. Mastering these power integrity design techniques will help you create high-performance, stable, and reliable six-layer board products. I hope this content has inspired you. If you enjoyed this video, please subscribe to my channel for more content. Thank you, everyone.